Hello, Mr. Fritz here again, and in these videos we're going to talk about generalizing the graph of the sine function. We're going to put all stuff together, we're going to give some rules, we're going to state some properties of these constants and how they affect the sine curve, and hopefully we'll get a little bit more comfortable with how to graph these things. So let's jump in and just talk about a little bit of a warm-up that I'd like you to actually try on your own. Pause the video and see if you can't match all of these graphs with their corresponding equations and their types of transformations. So there should be, for each one of these graphs, 1, 2, 3, 4, you should have 2 letters associated with each of them. One from this blob and then one from this blob. So pause the video, give this one a shot, and we'll talk about it in just a second. All right, and here are my answers down below. Hopefully you got something like that. If you didn't, then hopefully by the end of this video you'll get a good sense of what these transformations do as far as their equations and how they impact the graph. If I have some sine function in this format, f of x equals a times the sine of b times the quantity x minus c plus d, this is what's going to come out of it. One thing to note here is that this entire quantity here is all part of the sine function. So I don't have the parentheses there, you won't always see them, but it is implied that that's part of what's the input of the sine function. So this function here has an amplitude of a. Whatever that a value is, that's the amplitude. And remember, that is the distance from the midline to the max, or similarly to the min. So that is the distance from the top of the wave to the center of the wave. So that's a. All right, next let's talk about the period. The period of this function is going to be equal to 2 pi over whatever the b value is. And so remember, that period is the distance, or the x value that's needed to complete one full wave. So we'll say that's one full wave. So whatever this value is, once you divide by b, that shows you how long your period is. Okay, and next up, let's talk about the phase shift. The phase shift is going to be given by whatever the c value is, and so I'm shifting by a positive c. And one thing to note is that the c in the general form, I'm subtracting c, and I'm shifting positive c. And so the real takeaway there is that whatever I'm adding or subtracting by, I'm doing the opposite, moving the opposite direction. So like if I had a minus pi over 2 inside of here, I'm actually moving to the right pi over 2. So that's one thing to keep in mind. I'll say that's like moving my starting point. And the tricky thing is there isn't really like one starting point for these waves because they go on forever periodically, but I like to think of like 0, 0 as the original starting point for these sine functions. So in that way we can think of it as moving left or right from that initial starting part of the phase. And then finally we talk about the midline shift. Midline shift is equal to d. And so more specifically, that's y equals d. It gives you the midline equation. So that's pretty helpful. So if I'm adding 3 on the outside, then my midline is y equals 3. If I'm subtracting 3, my midline is y equals negative 3. And one thing to note is that this d doesn't have to be on the end. It could have been moved to the front. I could have said this is negative 3 plus 2 sine whatever, and that still makes that phase shift, or that midline shift, drop down or up, whatever corresponding to whatever value that d is. Last piece of this function is these key x values. I really kind of think them actually as like key x intervals. So maybe I'd even change that to key x intervals. And the way that you find that is you take your period and you divide it by 4. So by chopping it up into 4 sections, you're finding what your key intervals are between all of your plotted points. And so I'll show you what that means in a second. But for an example, if I had a period of equal to pi, then my interval would be pi over 4. That would be the spacing between each one of my key values that I use. Okay. One more thing to note, well, 2 things to note. In general, we have this graphing pattern, and we want to keep a mindset of how this graph normally moves from left to right. In my typical sine curve, it looks something like this, from 0 to 2 pi. And when I think about my key values, all of these are my key values. These are my x values once I chop up my period into 4 pieces. So in this case, the interval is pi over 2, pi over 2, pi over 2, pi over 2. And in general, whatever that first x value, key x value is, which is like my starting point, I'm at my midline. Normally starting at 0, 0, but that midline can move up or down, so I'll say I'm starting at my midline. My second value is my max. Wherever my maximum is, I go up to there. My next key value is back down to the midline. And then I continue to go downwards to the minimum, then back up to the midline. As long as we remember that this pattern of starting at the 0 or the midline, going up, coming back down, and then coming back up, back to the midline, then you can graph any one of these things with transformations in it. Last thing to note is about this b value. Sometimes you'll see a different format for this type of equation. Think about it, what would happen if I distributed this b value? It would look something like this. I could push that b through to this, and the other form would be f of x equals a times the sine of bx minus c plus d. And the only thing we need to keep note of is, minus bc. Yeah, I have to push that b through there. What makes this tricky is that now I'm not looking at my phase shift anymore. C doesn't give it to me, but I actually have b times c. So if I want to find what that phase shift is, which is c, I'm going to have to factor out b to get the phase shift. So for example, if I had y equals sine of 2x plus pi, I would need to factor out that 2 to get me sine of 2 times x plus pi over 2. Now that I've factored that out, I can see that my phase shift is negative pi. So we're going to take all of this and we'll take a look at a couple of examples in the next video.